now let's do one example on computing the eigenspace and finding the geometric multiplicity of a given matrix actually. So first we will find the eigenspace of for a given matrix. First we will find eigenvalues, then we'll see that what is the eigenspace of the matrix A, and then we'll try to find its dimension, which is going to be the geometric multiplicity of it actually. Or the other way that we propose, for example, from this method is that the G lambda, okay, is going to be the order of the matrix n by n matrix, so it's n minus the rank of the matrix A minus lambda I. So if you can compute this, you're still gonna get the geometric multiplicity. So let's do an example. So consider a 2 by 2 matrix. Okay, consider a 2 by 2 matrix which goes like 1 1 0 1. Okay, and what we would like to find is that what is the eigenspace of this matrix and what is the geometric multiplicity. Let's first find, for example, its eigenvalues. In order to find the eigenvalues, we need to solve this system x equal to, what do you call, lambda x actually. So if I take, say, x to be x1, x2, so let's solve this system. So when you're going to multiply this with the matrix, so row multiplied with column, you're going to get x1 plus x2 equal to lambda times x1, okay? And the second is going to be 0 1 multiplied by this, so x2 is equal to lambda times x2, okay? This is what that you're going to get. And from the second equation we can deduce that if the x2 is arbitrary, then lambda must be equal to 1 actually, okay? And if you, for example, substitute say lambda equal to 1 in the first equation, what does this is going to give you is that your x2 is 0 actually, okay? So the x2 is 0. So the eigenvectors corresponding to the value lambda 1 is really x1, x2, in other words x1, 0. And what would be the eigenspace associated with this matrix actually? So the eigenspace associated with this eigenvalue lambda equal to 1. By the way, there is no other way that you can have any other value actually. So the spectrum, you can explicitly say that the spectrum of the matrix A is this set 1 actually. So what would be the eigenvalue associated with the matrix A? So it's a collection of the vectors for which you have Ax equal to lambda x. But lambda is 1. So it's a collection of the vectors for which Ax equal to x actually. Okay? And which are those vectors for which you're going to get Ax equal to x? So these are the vectors. So you can simplify that this is going to be, these are the vectors for which x1 plus x2 is x1 and x2 is x1. So therefore x2 is 0. So in other words, these are the kind of vectors, okay? If x has a description of x1, x2, then x2 is equal to 0. So in other words, the eigenspace of the matrix A is corresponding to the eigenvalue lambda are the vectors of the form x1, 0, where x1 is really a real number actually. So therefore I can say that it's the span of the vector 1 0. So it's the span of the vector 1 0 transpose actually. Okay, so this is really the eigenspace of the matrix A. What is n in this case? So we are living in, so this is the matrix in M2 of R, so my n is 2. Okay, so now I would like to find the geometric multiplicity. So what is the geometric multiplicity? Okay, the geometric multiplicity is going to be the dimension of the eigenspace of A corresponding to the eigenvalue lambda. So the G1 is really, so how many vectors are spanning this eigenspace? So there is only one vector, so this must be equal to what you call 1 actually. By the way, you can also deduce from this identity that if the geometric multiplicity is 1 and n is 2, the rank of the matrix A minus I is going to be equal to 1. The other way to find the geometric multiplicity is that compute the rank of the matrix A minus lambda I, which is going to be A minus I in our case, and then subtract that rank from what do you call 2 actually, because n is 2. So that is, so you're going to see again that the geometric multiplicity is going to appear 1. Is the next important question. The next question that quickly we would like to answer, and then we would like to move to a new topic, is that if, so the question is if, is eigenvalues of a matrix A and A transpose are same. Okay, so is the eigenvalues of matrix A and A transpose are same? The answer is yes actually. Okay, obviously the matrix A is the matrix n by n matrix, it's a square matrix actually. The answer is yes. I mean, in our previous lecture, the first result that we proved was that if lambda is the eigenvalue of the matrix A, it is also an eigenvalue of the matrix A transpose actually. So really, the next interesting question would be that, okay, the eigenvalues are same. So if I have some eigenvalues, n eigenvalues that are the eigenvalues of matrix A, then they are also the eigenvalues of A transpose. Okay, so just go back, see the previous lecture, I think the first video, and there we proved a theorem actually where we said that if there is a number which is eigenvalue of the matrix A, it must be an eigenvalue of the A transpose as well. You can ask the next question. Okay, so here is the interesting lemma. So it says if you have an n by n square matrix and say lambda is from the spectrum of the matrix A, then the dimension of the eigenspace of the matrix A associated with the eigenvalue lambda is same as the dimension of the matrix A transpose associated, the dimension of the eigenspace of A transpose associated with the eigenvalue lambda actually. Okay, so we already know they are same, so this is another interesting observation. Why this would be the case? I can say that let's explicitly compute the dimension of the eigenspace of the matrix A associated with the lambda, which is same as the dimension of the null of the matrix A minus lambda I, and from that conclusion I can say that this is same as n minus the dimension, or maybe the rank of the matrix A minus lambda I, okay? But the rank of the matrix A minus lambda I is same as the rank of its transpose actually. So in other words, transposing a matrix does not changes its rank actually. So the rank of A minus lambda I is same as rank of A minus lambda I transpose. which is same as A transpose minus lambda I transpose, but I is identity matrix, it's a symmetric matrix, so its transpose would stay same. So I can say the transpose of A minus lambda I is going to be the transpose of A transpose minus lambda I. And if this is the case, this is same as the null space of, or maybe the dimension of the null space of A transpose minus lambda I. Okay? Because of the same result again actually. So if this is the case, then this shows that the dimension of the eigenspace of A transpose matrix associated with lambda A, they both are equal actually. Okay? They both are equal. And if they both are equal, you know, they are spanned by, so what we can say is that they, you know, even these eigenspaces are same actually. Okay, so even these eigenspaces are same. So that's really is another interesting observation that you can have about the eigenspaces. Next, now we're gonna move towards a new set of questions actually. So suppose you have been given a matrix A, which is a square matrix with entries from field, okay, which could be set of complex numbers and real numbers actually. So we saw basically previously that, you know, in order to find the eigenvalues and eigenvectors of a matrix A, you have to basically solve a system of equation actually. Question: is there another systematic way? Is there a systematic way to find the eigenvalues of A? The answer is yes actually. Okay, the answer is yes, and probably you already know it from your first linear algebra course, that magical thing that is going to give you the all eigenvalues is so-called characteristic polynomial. Okay, characteristic polynomial. So we'll see that what is characteristic polynomial, how to find it, and why the roots of the characteristic polynomial are eigenvalues. So if there is eigenvalue, it must be root of characteristic polynomial, and the all root of characteristic polynomials are eigenvalues. Okay, this is what is going to be the one systematic way. So in other words, whenever you have to try to find the eigenvalues of a matrix, see what is its characteristic polynomial and solve it. So whatever the roots of the characteristic polynomial are going to be the eigenvalues of the vector of the matrix A actually. But yes, in order to find the eigenvectors corresponding to eigenvalue, say lambda, you have to solve this system actually. Okay, we have to solve this system for finding eigenvector x actually. Okay, so this is what that we will like to do. So we like to study characteristic polynomial, its basic properties, and you know, some examples of it actually. What would be the second question, for example, that I will be interested in? That when a matrix A, is diagonalizable. Okay, so can I diagonalize a matrix? And if yes, how can I know that whether a given matrix is diagonalizable or not? So we will talk about the different criteria actually. Actually, we're going to see that, I mean, what is the good thing about the diagonal matrix actually? The good thing about the diagonal matrix is that for such matrices, it is really easy to compute the higher powers. So for example, if you have a 2 by 2 matrix, AB0, and I say you that, okay, compute the 100 power of this matrix actually. Okay, so you have one way that, okay, apply your algorithm actually to solve, to compute this 100 power. But you can see that for the diagonal matrix, it is really easy to just compute the A power 100, 0, and B power 100 actually. Okay, so computing the higher power of diagonal matrices is really easy. What is the meaning of, I'm going to define it, what do you call properly, that what is diagonalization and when a matrix is diagonalization, but let me just give you a glimpse actually that why this is going to be a very interesting topic. So a matrix is diagonalizable if you can write this matrix as a conjugate of a diagonal matrix. If you can write this matrix as, say, S inverse ds actually, okay? So if you can, where D is some diagonal matrix, okay? D is some diagonal, it's a diagonal matrix. I'm going to say A is diagonalizable if we can find a matrix S, okay, such that A can be written as S inverse diagonal matrix multiplied by S. So if A can be factorized in such a manner where D is diagonalizable, where D is diagonal matrix, we're going to say that matrix A is diagonalizable. Now what is the benefit of expressing A in the terms of such format? The key benefit is this. So for example, if you want to compute A square, so what would be A square? So if A is factorized in this manner, we can say that you have S ds times S inverse ds. Okay, I can apply associative law. S and S inverse will get cancelled. Okay, and you're gonna get S inverse d square S actually. Okay, so the A square is going to be S square, S inverse d square S. Hence, A power n you can show is really easy, S inverse d power n S. So diagonalizable matrices are the kind of matrices whose higher power, okay, whose higher power are really easy to calculate. If you can diagonalize a matrix in the terms of some matrix and diagonal matrix, then its higher power can be computed easily by this formula. Since D is a diagonal matrix, so you can easily quickly compute its, its power. And the D power n is going to be that, okay, take their diagonal entries and compute their power n and multiply them with S inverse and S, and that is going to give you A power n actually. Okay, A power n. So this is what the benefit of this is going to be. You're going to see actually, so when we're going to talk about what you call the Google PageRank algorithm, previously the Google was using this algorithm to, do the Google search actually. So if you are using, for example, if you are searching something on Google, some years back you were using the Google PageRank algorithm. Now when the Google algorithm is making a search actually, it is actually computing the higher powers of a given matrix. So it computes the higher powers of the given matrix. And why, that algorithm is, easily, computing the higher power of the matrix, okay, consisting of the information about the websites, okay, because the matrices, considered there or in that algorithm are somehow diagonalizable actually, okay. So this diagonalization has huge implications actually in modern sciences actually. So we're going to talk about when a matrix is diagonalizable, what are some of the criteria of it actually? So this is what is going to be the next question that we would like to ask. The next question that would be is that if you have a function, so I know that for a polynomial, so if I take a polynomial p, the p of a makes sense actually, okay? So p evaluated at a makes sense. But what if my function is not a polynomial, it's like e to the x. It's like, you know, it's like sine x actually, okay, or sine square x, something like that. The question is, does f of a going to make sense? In other words, if e to the a is some object, is sine square a valid object? Okay, we're going to see that if your matrix is diagonalizable, you know, even you can do the functional calculus with the matrices actually. Okay, you can do the functional calculus with the matrices. So all these are going to make sense if A is diagonalizable. And we will see some of applications of the diagonalizability as well actually. Okay, so we're going to see some of the applications of diagonalizability. So this is really is some of the glimpse of the things that we're going to do in maybe today's discussion, or maybe some of the things we're going to cover in tomorrow's discussion actually.